This is the first of 3 experiments dealing with chemical reactions. We'll begin with an overview of the types of chemical reactions, and then in this first video we'll look specifically at combination reactions, combustion reactions, decomposition reactions, and double displacement reactions.
Combination reaction, called a synthesis reaction, is one in which simpler substances combine into a more complex compound. Here's a generic example. Substance A combines with substance Z to produce compound AZ. And here's a specific example. Calcium metal reacts with chlorine gas to produce calcium chloride, a salt that's used for de-icing roads. A decomposition reaction is one in which a single compound is broken down into 2 or more simpler substances, often by heating the starting material. Compound AZ, on heating, can be broken down into substance A and substance Z. For example, calcium chloride, heated in the absence of oxygen, can be decomposed into calcium metal and chlorine gas. So decomposition is pretty much the opposite of combination. A single replacement reaction, often called a redox reaction, is one in which a more reactive element displaces a less reactive element's ion from a compound or from aqueous solution. So A reacts with BZ and displaces B, forming AZ. For example, zinc metal reacts with copper 2 sulfate and displaces copper and forms zinc sulfate. A double displacement reaction, called a precipitation reaction, is one in which 2 compounds exchange cations and anions. AX reacts with BZ, forming AZ and BX. For example, silver nitrate reacts with sodium chloride, forming silver chloride and sodium nitrate. A neutralization reaction is one in which an acid reacts with a base, producing salt and water. So here's a generic acid, HX, reacting with a generic base, BOH. The hydrogen ion from the acid reacts with the hydroxide ion from the base, producing water, and the cation from the base, B, and the anion from the acid, X, combine to form a salt, BX. Specifically, HCl reacts with sodium hydroxide, the hydrogen and hydroxide form water, the sodium ion and chloride ion form sodium chloride, a salt. And finally, a combustion reaction is one in which a fuel that contains carbon and or hydrogen burns in oxygen and produces carbon dioxide and or water. For example, methane reacts with oxygen to produce carbon dioxide and water. Number 1, combination reactions, synthesis reactions. Now there are many examples of combination reactions. We're going to look at just 3 types. First, we'll look at the combination of a metal and oxygen gas producing a metal oxide salt, which is an ionic compound. Second, the combination of a nonmetal and oxygen gas producing a nonmetal oxide, which will be a covalent compound. And finally, the combination of a metal and a nonmetal other than oxygen, and that will produce an ionic salt. So first, the combination of a metal and oxygen gas producing a metal oxide salt. Let's consider magnesium metal. It burns in air, emitting a brilliant white light, and produces a gray-white magnesium oxide ash. Here I have the Lewis symbols of 2 magnesium atoms. Recall that magnesium is a group 2A metal that desperately wants to empty its valence shell by losing its 2 valence electrons. We also see the Lewis structure of an oxygen molecule. And recall that oxygen is a group 6A nonmetal that desperately wants to fill its valence shell by gaining 2 more electrons. So this is a happy combination in which magnesium atoms lose both their valence electrons, forming Mg plus 2 cations, and the oxygens gain 2 electrons, forming oxide minus 2 anions. This is an ionic compound. Let's watch this reaction. I'm going to use the heat of a Bunsen burner flame to initiate the burning of magnesium metal turnings in air. Now, this is a combination reaction in which magnesium metal combines with oxygen gas, producing an ionic compound, magnesium oxide. Now, the literature says the temperature of this reaction exceeds 3,000 degrees Celsius, and I believe that based on the intensity of the white flame. And I also noticed at the end of the reaction that some of the surface of the watch glass was melted. At the end of the reaction, we see we have a white ash of magnesium oxide, an ionic salt. So here's the chemical equation for that. 2 magnesium plus O2 produces MgO. It's a combination reaction. Now we can usually predict the formulas of metal oxides containing A group metals because most of the A group metals have only a single oxidation state. We usually cannot predict the formulas of metal oxides that contain transition metals because most of the transition metals have more than one oxidation state. And so for transition metal oxides, the ionic charge of the metal must be given in order for the student to be able to write the chemical formula of the metal oxide. All right, let's get some practice writing balanced chemical equations. Aluminum metal reacts with oxygen gas. You may need to refer to the periodic table to get the symbols that correspond to the names. The symbol for aluminum is Al. The symbol for oxygen, of course, is O. So we can write aluminum plus O2. Now you need to recall that oxygen is one of the 7 diatomic elements and exists as pairs of atoms, molecules, O2. Recall that all the metals are all monatomic and they're always written as single atoms. Now to get the product, it'll be aluminum oxide, but what's its formula? You'll need to combine the cations and anions in appropriate ratios. So we can see from the table that aluminum is always plus 3, oxide is always minus 2. If we use the inverse rule, it tells us that the charge of the anion becomes the multiplier of the cation, and likewise the charge of the cation becomes the multiplier of the anion. And the formula Al2O3 satisfies the requirement that the total positive charge is equal to the total negative charge. So 2 times plus 3 is plus 6. 3 times minus 2 is negative 6. So that's the correct formula of aluminum oxide. And finally, we need to balance the equation. Notice I have 3 oxygens on the right. It's an odd number, but only 2 oxygens on the left, and that's an even number. The easiest way to handle odd and even numbers is typically to double up on the odd number. That gives us an even number of oxygens, which is 6, and so the other even number will now divide evenly into it. So 2 goes into 6 3 times. So 3O2 and 2Al2O3. All that's left is to balance the aluminum, and a 4 on the left will do that. Let's try zinc metal reacting with oxygen gas. The table tells us that the symbol for zinc is Zn, and we know what oxygen is, so we can write zinc plus O2. Now again, we need to combine zinc and oxygen in the correct ratio. Well, zinc you can see is only plus 2 and oxygen is minus 2, so these will combine in a 1-to-1 ratio of ZnO, zinc oxide. To balance this, we simply need to double up on the zinc oxides, and now oxygen is balanced, and now we'll double up on the zinc, and zinc is balanced. How about iron metal rusts when exposed to air, producing iron 3 oxide, which is rust? Well, iron is one of the transition metals, and notice it has more than one oxidation state. Fortunately, the name tells us what the oxidation state is in the product. Oxides minus 2. So we can write iron plus O2. Now, what's the formula for iron 3 oxide? Well, we need to combine the ions and their charges. Iron is plus 3, oxides minus 2. Once again, if we take the charge of one ion and make it the multiplier of the other ion, both ways, we'll find by the inverse rule the formula for iron 3 oxide is Fe2O3. Notice again, the total positive charge, 2 times plus 3 is plus 6, will be equal to the magnitude of the total negative charge. 3 times minus 2 is negative 6. To balance this, we need to double up on the Fe2O3. Gives us an even number of oxygens, 6, and 2 divides evenly into it 3 times, and we'll need 4 irons on the left, and we're good to go.
Let's take a look at this reaction. Iron plus oxygen to produce iron oxide. Just need a little heat to get it started. That looks like pyrotechnics, doesn't it? Guess what? That's what pyrotechnics is. A metal plus oxygen producing a metal oxide.
Next, we're going to look at the combination of a nonmetal and oxygen gas. In this type of combination reaction, a nonmetal reacts with oxygen producing a nonmetal oxide, a covalent compound. For example, when carbon burns completely in the presence of oxygen gas, carbon dioxide is formed. Recall that carbon's in group 4A, has 4 valence electrons, and will form 4 bonds with another nonmetal to fill its valence shell. And oxygen in group 6A will form 2 bonds with another nonmetal to fill its valence shell. So the combination of carbon and oxygen producing carbon dioxide provides a structure in which all atoms have their valence shells filled. Here's the chemical equation. It is simply carbon plus O2 produces CO2. Nonmetal oxides can occur in multiple combining ratios. For example, carbon dioxide, CO2, and carbon monoxide, CO, can both form by combination reactions. So usually the formula of a nonmetal oxide product is not predictable. It varies with the temperature, the pressure, and the ratio of combining atoms. A particular extreme case is nitrogen combining with oxygen, giving all the various nitrogen oxide compounds. For example, nitrous oxide, nitric oxide, dinitrogen trioxide, nitrogen dioxide, dinitrogen tetroxide, and even dinitrogen pentoxide. All right, let's get some practice writing chemical equations for nonmetals combining with oxygen gas. Carbon burns incompletely, producing carbon monoxide. Symbol for carbon is C and oxygen is O. Now in this case, we don't need to use the oxidation numbers to find out the formula of the product because the name tells us it's a 1-to-1 ratio. So we have carbon plus diatomic oxygen producing CO. All we have to do is balance that. We'll put a 2 in front of the CO and then a 2 in front of the carbon and we're good. How about sulfur forming sulfur trioxide when burned in excess oxygen gas? Sulfur is the symbol S, oxygen is O. So we can write S plus O2. Once again, we don't need the oxidation numbers to write the formula of the product because the name tells us it's sulfur trioxide. We have an odd number of oxygens on the right and an even number, so if we double up the number of oxygens on the right, it's now even. That's 6 oxygens times 3 on the left balances the oxygens and 2 sulfurs. Let's take a look at this reaction. When yellow sulfur is melted in a Bunsen burner flame, it forms a dark orange viscous liquid. On continued heating, the viscosity reduces and the liquid becomes thin and can be poured. When ignited, sulfur burns with a bright blue flame, producing a mixture of non-metal oxides, sulfur dioxide and sulfur trioxide. All right, one more. Nitrogen is converted to nitrogen dioxide in an automobile engine. So nitrogen is the symbol N, and of course oxygen is O. We can write N2 plus O2. Recall that both nitrogen and oxygen are diatomic elements. Once again, we can get the formula of the product simply from the name. Nitrogen dioxide is NO2. And to balance this, we see that we need to balance the nitrogen, and that's then the oxygen. And we're done. So the last combination reaction we're going to look at is that of a metal and a nonmetal other than oxygen. That would produce an ionic salt. Let's look at a familiar example of sodium metal, which reacts vigorously with chlorine gas to produce heat, light, and sodium chloride. Recall that sodium is a reactive group 1A metal that desperately wants to lose its one valence electron and empty its valence shell, and chlorine is a reactive group 7A nonmetal that wants to gain one electron to fill its valence shell. So this is a happy, or should I say vigorous reaction in which sodium loses an electron to form sodium cations, chlorine gains an electron to form chloride anion, and would produce sodium chloride, an ionic salt product. Here's the balanced equation. Simply 2Na plus Cl2 produces NaCl. And here we're talking about the formation of good old table salt, sodium chloride. If the compound contains an A group metal, then the formula is usually predictable because most of the A group metals have only one oxidation number. But if the metal has more than one possible oxidation number, then more than one formula is possible, so the student would have to be told the name of the product to write the equation. So let's balance a few equations involving metals and nonmetals. How about aluminum metal reacting with sulfur? We need the symbols of aluminum and sulfur. From the periodic table, we see that the symbol of aluminum is Al, and the symbol for sulfur is S. We can simply write Al plus S. Now I'm just going to use the monatomic form of sulfur. I know it exists in a variety of polyatomic forms, but we'll keep it simple for this first course. So we need to write the product, and that will be aluminum sulfide. But what's the formula of aluminum sulfide? Well, aluminum is in group 3A. That's always plus 3. Now sulfur has 4 different oxidation states. Which one do we use? Well, it's an ionic compound, which means that aluminum is the cation, sulfur is the anion. We have to use its negative charge, which is -2. We can use the inverse rule to determine the formula of aluminum sulfide. That'll be Al2S3. And since I've used monatomic reagents, that should be very easy to balance. Next we have a magnesium reacting with monatomic phosphorus. So the periodic table again will tell us the symbol of magnesium is Mg, and the symbol for phosphorus is P. We can write Mg plus P, and again I'm going to use the monatomic form of the nonmetal to keep it simple for us. Now we need the formula for magnesium phosphide. Look at the periodic table. Group 2A metals are always +2 oxidation number. For phosphorus, we want to use its negative oxidation number because it's going to be an anion when combined with a metal. We can use the inverse rule to obtain the formula of magnesium phosphide. It'll be Mg3P2. And again, since I have monatomic reactants, it's easy to write the correct balanced equation for that. Last example here is potassium metal reacting with iodine to form potassium iodide. What are the symbols of potassium and iodine? Well, K is the symbol of potassium, and I is the symbol of iodine. So I can write K plus I2. And you must remember that iodine is one of the 7 diatomic elements. It exists in bonded pairs of atoms, so write I2. Now what about the formula of potassium iodide? Well, the charge of iodine, group 1A metal, is always +1, and the charge of the anion of iodine has to be -1. So they will combine in a 1-to-1 ratio, potassium iodide. Now I have 2 iodines on the left. I'll need to put a coefficient of 2 in front of Ki, and that gives me 2 potassiums on the right. I'll need to put a coefficient of 2 in front of K on the left. And that takes care of it.
Let's take a look at the reaction of a non-metal. This is iodine that I've ground up with a metal. This is magnesium turnings. On first contact, no reaction at room temperature. I'll mix it together and see if that'll get it started. Not looking good. I'll either have to heat this or initiate it somehow. I'm going to try a drop of water first, and if that doesn't work, then we'll heat it. Now I can see a little bit of bubbling. Okay, it started, but it seems to have subsided. Let's try more water. That's looking better. So the purple vapors, that's not magnesium iodide, that's iodine. Iodine sublimes from solid to gas. It's a purple vapor. The reaction seems to have stalled out again. The crucible is not hot to touch. I'm going to try more water still. Well, that's looking better. So magnesium iodide is a white crystalline solid. All I see is purple-black goo. That's likely the excess iodine that's present. So there's the reaction of a metal, magnesium, with a non-metal, iodine, to produce a metal, non-metal salt, magnesium iodide. The second type of chemical reactions we'll look at are combustion reactions.
When combustibles or flammable materials burn, these materials, called fuels, are reacting with oxygen in the air. The simplest examples of combustion reactions are those involving pure hydrogen or pure carbon. When hydrogen burns, it produces water, H2O. And when carbon burns, at least with sufficient oxygen, it produces carbon dioxide. A hydrocarbon, often abbreviated HC, hydrocarbons are organic compounds that contain only hydrogen and carbon. Hydrocarbons are flammable in air, and many are used as fuels. Laboratory gas is generally a mixture of light hydrocarbons such as methane or propane, and when it burns, it liberates carbon dioxide and water. Now, some fuels, like alcohols, for example ethanol, also contain oxygen. Let's take a look at a few common fuels. Acetylene, C2H2, is commonly known as welder's fuel. Methane, CH4, is the simplest of hydrocarbons, and it is the main component of natural gas. Propane, C3H8, is known as barbecue fuel. Butane, C4H10, is cigarette lighter fuel. And octane, C8H18, is the main component of gasoline. Here's an alcohol. Ethanol, C2H5OH, is both a fuel itself and a gasoline additive. Well, provided that enough oxygen is supplied, complete combustion occurs, and the products of complete combustion of carbon, hydrogen, and oxygen are carbon dioxide and water plus energy. Let's balance the following combustion reaction equations. Propane, C3H8, when burned in air, combines with oxygen, producing carbon dioxide and water. Whenever you balance a chemical equation of any sort, it's always best to leave the simplest formulas to the very end. For example, O2 is the simplest formula. When I put a coefficient in front of the oxygen, it doesn't affect any element but itself. However, when you put a coefficient in front of propane, you're going to change both the number of carbons and hydrogens in the entire equation. So start with the propane and leave the oxygen to the end. So I see 3 carbons on the left and only 1 on the right, so let's put 3 in front of CO2 and the carbon is balanced. There are 8 hydrogens on the left and 2 on the right. Put a coefficient of 4 in front of H2O and we have 8 hydrogens on both sides. Let's move to the right and count our oxygens. 3 times 2 is 6 for the CO2, plus 4 from the H2O makes 10 oxygens on the right. So on the left-hand side, I need to have 10 oxygens. How do I get that? Let's put a coefficient of 5 in front of the O2, and that gives us 10 oxygens on both sides. How about methanol? CH3OH, burned in air, combines with oxygen to produce carbon dioxide and water. Now the carbon is already balanced, so let's move to the hydrogen. On the left side I have 4 hydrogens. On the right side I have 2, so I put a coefficient of 2 in front of H2O and the hydrogens are balanced at 4 apiece. Now on the right hand side I have 2 oxygens from the CO2 and 2 from the water, giving a total of 4 oxygens. On the left hand side I have 1 oxygen in the methanol. I don't want to change that because that'll change everything. And I need 3 more oxygens coming from the O2. Now how does O2 become 3 oxygens? Well, the easiest way is to use a coefficient of 3/2, because 3/2 times 2 is equal to 3. And this equation is now balanced. The problem is we don't use fractional coefficients. We always want to use the lowest set of whole number coefficients. To get rid of the fraction, we can multiply this by 2, because 3/2 times 2 is 3. But if we do that to the oxygen, we have to do it to all the terms to keep the equation balanced. Let's multiply everything by 2. That'll give us 2 methanol plus 3 oxygens. Remember, 3/2 times 2 is 3. And 2 CO2 and 4 H2O. And if you check, all elements are balanced in this equation. This is methyl alcohol, also known as methanol. Now, methanol has a low boiling point. It's 65 degrees Celsius, which means it's very volatile. It's easy to ignite. So the first contact with a flame should get it started. There it goes. Notice the flame is pale blue, almost invisible. Now, it burns with a clean flame because there's no evidence of any glowing carbon particles. There's no soot. And in that regard, it's a very good fuel. Let's balance next the combustion of octane, C8H18, in air, combines with oxygen to produce CO2 and water. On the left I have 8 carbons, so on the right I'll need 8 CO2s to balance the carbon. On the left I have 18 hydrogens, so on the right I'll put a 9 in front of the H2O to balance the hydrogens. So now let's count the oxygens on the right side. 8 times 2 is 16, plus 9 makes 25 oxygens on the right. So on the left, I also need a total of 25 oxygens. And how do I get that? Well, O2 has to become 25. The easiest way is to use a coefficient of 25 over 2. This equation is now balanced, but it's not in the proper form. Let's get rid of the fractional coefficient, but retain the balance, so multiply all terms by 2. That'll give me 2 moles of C8H18 and 25 O2, so 25 halves times 2 is 25 O2. 8 times 2 is 16 CO2, 9 times 2 is 18 H2O, and this equation is now balanced. This is octane, C8H18. It's not nearly as volatile as methanol. Its boiling point is quite a bit higher. It's around 125 degrees Celsius, and so it's going to take a little more heat to get it to start to burn. Now that we see it burning, you can see an incandescence, which indicates it doesn't burn as cleanly as methanol. The orange incandescence is the result of unburned carbon particles that are glowing in the flame, and for that reason octane may burn cleanly in an internal combustion engine, but is not nearly as well suited for use in an open flame or an alcohol lamp. Okay, so whenever you are finished balancing an equation, it's always a good idea to, at least mentally, if not on paper, to check that in fact all the atoms do indeed balance, are equal on both sides of the equation. So for each element, let's count them up. So for carbon, on the left side I see 2 times 8 or 16 carbons, and on the right I see 16 carbons in the CO2. For hydrogen, I see 2 times 18 or 36 hydrogens on the left, and I see 18 times 2 or 36 hydrogens on the right. Now for oxygen, I have 25 O2, and that's 50 oxygens on the left. On the right hand side I have 16 CO2 gives me 32 oxygens, and then 18 waters gives me another 18 oxygens for a total of 50 oxygens, and so we are in fact balanced.
This seems like a good time to show you how to light a Bunsen burner. First you want to check that the igniter can spark. Not much there. Open it up, look, there's not much flint left here, barely anything exposed. Let's try another one. Right, so there's flint, so that should light. You want to scrape that flint pretty hard against the back rough surface to get a spark. Right, before you turn on the gas, close the barrel, rightsy tightsy. You want to eliminate air entering into the barrel of the burner, and that way it lights much easier. So that's closed, the barrel's closed. Now turn on the gas jet. Now I'm going to listen. I put this to my ear and listen. If you can't hear any gas, it's not going to light, so open the valve at the bottom to allow more gas in, and then listen again. Okay, so if you listen and now you hear it, it should light easily. Good. Now, with the barrel closed and no air, it lights easily, but you don't want to run your burner like this. The luminous flame means there's unburned carbon particles, basically soot, that will deposit on your work. So you don't want to run it like this. I'm just holding the crucible here to show you the amount of carbon that will build up. This needs more air. Right, look at all that carbon. So once the flame is lit, then you raise the barrel, leftsy-loosey. Right, raise the barrel, that lets more air in, and the flame will burn more completely. I see some sparks of orange, yellow, that's some salt contamination in the burner. Ignoring that, that is a cool flame. If you want it hotter, then you want to raise the barrel and allow more air to come in, and it burns more completely still. Flame gets noisy, and you see an inner blue cone, and the tip of the inner blue cone, where I'm pointing with the crucible tongs, that's the hottest part of the flame. If you want it cooler, simply lower the barrel, rightsy-tightsy, and you have a cool flame, but not luminous. And that's it. The third type of chemical reaction we'll look at in this experiment is a decomposition reaction.
And there are many examples of decomposition reactions. We're only going to look at 2 types. First, the decomposition of a metal bicarbonate, and secondly, the decomposition of a metal carbonate. The decomposition of metal bicarbonates. A metal hydrogen carbonate, which is the same as a metal bicarbonate, will decompose on heating. For example, baking soda, NaHCO3, is a natural fire extinguisher. Heat from a fire will decompose baking soda, releasing water and carbon dioxide gas. And since carbon dioxide is denser than air and is non-flammable, it smothers the flame by excluding the oxygen. The decomposition of a metal bicarbonate yields a metal carbonate, water, and carbon dioxide. Let's take a look at the decomposition of a metal bicarbonate. The test tube on the left contains sodium bicarbonate, commonly known as baking soda. In the test tube on the right, I'm adding a saturated solution of calcium hydroxide called lime water. Calcium hydroxide is a strong base, and it's used to detect carbon dioxide. When the sodium bicarbonate is heated, it liberates carbon dioxide gas, And that carbon dioxide gas is being bubbled into the solution of lime water. Now, carbon dioxide reacts chemically with calcium hydroxide, precipitating calcium carbonate, CaCO3. Calcium carbonate is essentially limestone, and it's insoluble in water. And after some time, you can also see the buildup of water condensing in the top of the test tube on the left. And so we see that the decomposition of a metal carbonate releases carbon dioxide gas and water. And what's left in the test tube on the left, that white solid, is no longer going to be sodium bicarbonate, but it will be a metal carbonate, in this case, sodium carbonate, Na2CO3. So here's the chemical equation. 2NaHCO3 liberates 1 molecule of carbon dioxide, 1 molecule of water, and the metal carbonate, in this case, sodium carbonate. So you need to remember that 2 bicarbonate ions produce 1 carbon dioxide molecule, 1 water molecule, and 1 carbonate ion. Let's get some practice. This is magnesium bicarbonate. Magnesium bicarbonate is, when heated, will decompose into carbon dioxide and water and the metal carbonate, in this case magnesium carbonate. Now this one's easy to balance because magnesium is in group 2A, its charge is +2, and carbonate is -2, so they combine 1 to 1, and that equation is balanced. How about calcium bicarbonate? When heated, it decomposes, producing carbon dioxide and water, and the metal carbonate, in this case, calcium carbonate. And since calcium and magnesium are in the same group, they both have a charge of +2, it balances the same as the magnesium bicarbonate decomposition. Calcium bicarbonate is the major form of water hardness. When heated, it deposits as a white scale. And you might see this in the bottom of a kettle, and we see it industrially in boilers. All right, the last decomposition reaction we want to look at is that of the decomposition of a metal carbonate. So after a metal bicarbonate decomposes into a metal carbonate, the metal carbonate itself can be further decomposed with prolonged heating into a metal oxide and carbon dioxide. So for example, limestone is largely made of calcium carbonate. Limestone is mined, it's crushed and heated in kilns, these are high temperature furnaces, to produce carbon dioxide and a white powder known as calcium oxide, often called lime or quick lime or even dry lime. Note in the reaction that each carbonate ion produces 1 molecule of CO2 and 1 oxide O-2 anion. Now lime is a strong base and it's a component of cement and mortar. All right, your turn. Magnesium carbonate is a secondary component of limestone. Write a balanced equation for the decomposition of magnesium carbonate. We'd write magnesium carbonate decomposes into carbon dioxide and the metal oxide, MgO. Let's look at one more decomposition reaction. This will be the decomposition of hydrogen peroxide, H2O2. Oxygen is in group 6A and it is most stable when it has an oxidation state of -2. Hydrogen peroxide is an unstable compound in which oxygen has an oxidation state of -1. And so peroxide decomposes as shown. It decomposes into water and oxygen. Now this reaction is accelerated in the presence of potassium iodide, and the addition of some liquid dish detergent will add a little drama to the demonstration that we're about to see. Just a word of caution, 30% hydrogen peroxide will cause immediate and permanent eye damage, so safety glasses are an absolute must when doing this experiment. So the fourth type of chemical reaction is precipitation or double displacement, but we have to lay a little groundwork before we get there, and that's the solubility precipitation concept. Ionic compounds, that is, salts, are held together by strong electrostatic forces of attraction of oppositely charged ions. And that's what ionic bonds are, the attraction between cations and anions. So look at the formation of potassium chloride, ionic salt. Potassium metal is a reactive group 1A metal with one valence electron it wants to lose, and chlorine is a reactive 7A nonmetal that needs one electron to complete its octet. So they react, potassium giving its electron to chloride, forming potassium ions and chloride anions. We have a potassium chloride salt. Now the strength of these bonds results in a high melting point of ionic compounds, typically greater than 400 degrees C. In fact, in the case of potassium chloride, has a melting point of 772 degrees C and a boiling point of 1411 degrees C. That's a lot of heat required to separate these ions. They're strongly attracted. Amazingly, many ionic compounds are soluble in water at room temperature without heating. So here's potassium chloride salt. Put it in water at room temperature. The ions are separated into potassium cations and chloride anions. How does that happen? Well, when ionic compounds dissolve in water, their cations and anions are separated and they disperse in water, forming a solution at room temperature without heating. Take a look at this illustration. Here we have potassium chloride solid, solute. We put it in water, and then this represents what's happening in solution. The small, highly polar water molecules, here they are, they insert themselves between the positive and negative ions of this solute, separating the ions. The slightly negative or partial negative oxygen atoms move close to the solute cation, in this case potassium. They surround it. At the same time, the slightly positive or partially positive hydrogen atoms of the water molecules surround and move close to the anion, in this case chloride. In this way, water molecules effectively insulate the solute ions from each other, thereby making it easier for the solute to pass from the solid state into solution, that is, easier to dissolve. So continuing with the solubility precipitation concept, the process of a salt dissolving in water is shown by the following chemical equation. Here's potassium chloride solid, salt in water, separates into potassium cations and chloride anions, and the suffix aq means aqueous or dissolved in water. The solubility of ionic compounds as well as polar compounds is commonly described by the rule like dissolves like. Ions contain positive and negative charges, and water contains partial positive and negative charges, and in that sense, although they're not identical, they are alike. Now, while it's true that many ionic compounds are water soluble, some ionic compounds are actually insoluble because the force of ionic attraction between cations and anions of the salt are stronger than the attraction between water and the ions of the salt. And one example we're going to look at is that of a water-insoluble ionic salt called lithium fluoride. The solubility of lithium fluoride in water is only 0.27 grams per 100 mils. It's quite insoluble. Let's consider what happens when an aqueous solution of lithium iodide is mixed with an aqueous solution of potassium fluoride. So here I'm dissolving lithium iodide in water. Notice the solubility is very high, 151 grams per 100 mils of solution. That's a lot of lithium iodide. So it produces a clear colorless solution containing lithium ions and iodide anions. We can also make a solution of potassium fluoride, dissolving it in water. Notice the solubility is also very high, 92 grams of potassium fluoride per 100 mL of solution. So we get another clear, colorless solution containing potassium ions and fluoride ions. But what would happen if we mix these two solutions together? Well, the potassium ions would come in contact with the iodide ions, but they are very soluble, 148 grams per 100 mL of solution. But notice that lithium fluoride is not so soluble. When a lithium cation collides with a fluoride anion, they will combine together so strongly that water can't separate them, and they will immediately precipitate as a solid lithium fluoride. Its solubility is approximately 0.3 grams per 100 mL of solution. And lithium fluoride is thus a precipitate. Potassium and iodine ions remain in solution, and they are spectator ions. And this is a precipitation reaction. So looking further at this reaction, potassium fluoride reacting with lithium iodide precipitates lithium fluoride solid, and potassium iodide aqueous remains in solution. This is called the reaction equation. Let's take another look at it. Here is a clear colorless solution of lithium iodide, and in it I'm going to add a clear colorless solution of potassium fluoride. The solid that's coming out of solution is insoluble, or at least lithium fluoride of low solubility. Potassium iodide remains in solution. So if we take our reaction equation and break it apart, everywhere we have the suffix AQ, it really means that the salt is present as ions. So KFAQ on the left side is really potassium ions and fluoride ions. And lithium iodide AQ is really lithium ions and iodide ions. On the right side of the equation, we have lithium fluoride solid. Well, that can't be broken apart into ions because it isn't present as ions. It's a solid. But we do have potassium iodide AQ, which I can break apart into potassium ions and iodide anions. This big messy equation is called the ionic equation. If we leave out the spectator ions, the ones that don't react, and include only the ones that do react, we get a much tidier equation called the net ionic equation. So I've left out potassium ions and iodide ions on both sides since they're not really reacting, and I only include lithium and fluoride on the left and lithium fluoride on the right. The net ionic equation leaves out spectator ions and shows only the ions that react to form a precipitate. Solubility rules for precipitation reactions. Now it turns out that many ionic compounds are soluble in water, but then some are insoluble. In precipitation reactions, two aqueous solutions react to form a compound that is not soluble in water, and that is, it's a precipitate. We need a method of predicting when precipitates will form. Now the solubility of most inorganic compounds has been tested, and solubility patterns have been observed and are summarized in the following table. Now the solubility rules are not without exception, but they do hold in most cases. So first of all, we're going to list ions that are almost always soluble. For example, the group 1A ions, hydrogen through francium, and ammonium ion. They're virtually all soluble. Nitrate, perchlorate, chlorate, and acetate, all of these compounds made from these ions are typically always soluble. Exception, as we've just seen, is lithium fluoride. Lithium's a group 1A ion. Chlorides, bromides, and iodides, almost all their salts are soluble unless they're combined with lead-2, mercury-1, mercury-2, silver, in which case the halides are insoluble. Almost all sulfates are soluble unless the sulfate is combined with lead-2, mercury-1, mercury-2, silver, calcium, strontium, or barium, in which case they're insoluble, otherwise sulfates are soluble. And finally, virtually all fluorides are soluble unless they're combined with lead-2, mercury-1, mercury-2, or the group 2A ions, beryllium through radium, and of course lithium, which is a rare exception that we spoke of earlier. So those are the ions that are virtually always insoluble compounds. Now, what follows is a list of a couple groups of ions that are almost always insoluble. So almost all hydroxide compounds are insoluble unless the hydroxide is combined with ammonium or the group 1A ions or barium, in which case the hydroxides happen to be soluble. And finally, all chromates, all phosphates, all carbonates, sulfides, and sulfites, they're all insoluble in any of their compounds unless they happen to be combined with ammonium or the group 1A ions, in which case they're soluble. And we define solubility in this way. Less than 1 gram per liter is considered insoluble. Slightly soluble is 1 to 10 grams per liter, and soluble is less than 10 grams per liter. Solubility rules for precipitation reactions. Let's get some practice. So for each of the following compounds, I'd like you to predict whether they are soluble or insoluble. And you can use the symbol AQ, meaning soluble, or S for insoluble or solid. First of all, potassium nitrate. We've just seen that all nitrates and all group 1A ions, of which potassium is a member, are soluble, so certainly potassium nitrate would be a soluble compound. How about sodium carbonate, Na2CO3? Well, it's true that most carbonates are insoluble, but when combined with the group 1A ions, like sodium for example, they're soluble. Ammonium phosphate. We saw that all phosphates are insoluble unless they're combined with one of these exceptions, and ammonium is one of those exceptions, and so ammonium phosphate is also soluble. How about calcium carbonate, CaCO3? We've seen that almost all carbonates are insoluble, and the only case where it's not is when the carbonate is combined with ammonium or the group 1A ions. Well, calcium is not one of those exceptions, and therefore calcium carbonate is in fact insoluble. Calcium carbonate is limestone. It's not soluble. Try the next group, magnesium sulfate. Well, we've seen that all sulfates are soluble unless they're combined with lead, 2, mercury, silver, calcium, strontium, or barium, in which case they're insoluble. Well, magnesium is not one of these exceptions, and so magnesium sulfate would in fact be soluble. How about aluminum hydroxide? You see from the table that all hydroxides are insoluble unless they're combined with ammonium, barium, or group 1A ions. Well, aluminum is not one of those exceptions, and therefore aluminum hydroxide will in fact be insoluble. How about iron 3 chloride? Well, we saw up here that all chlorides are soluble unless they're combined with lead, 2, mercury 1, mercury 2, or silver. Now, iron is not in that list, and therefore iron 3 chloride must be soluble. And finally, how about barium sulfate? We saw that all sulfates are soluble unless they're combined with lead, mercury, silver, calcium, strontium, or barium. Well, it turns out that barium is one of the exceptions. Barium sulfate happens to be insoluble. Okay, let's get some practice. Let's combine aqueous silver nitrate with aqueous sodium chloride. Both of these are soluble. Let's interchange ions. The brown line connects the inner ions, so when sodium ion meets nitrate ion, well, we know that from group solubility rule number 1 that all nitrates are soluble and all sodium salts, group 1A ions, are soluble, so certainly silver nitrate is soluble. But what about silver meeting chloride? Well, rule number 2 tells us that all chlorides are soluble unless chloride is combined with lead, 2, mercury 1, mercury 2, or silver. So there it is. Silver chloride happens to be insoluble. So we can write the products NaNO3 aqueous and silver chloride solid precipitate. Now it turns out that this equation is balanced because all of the ions have a charge of magnitude 1. So both silver and sodium have a +1 charge, and nitrate and chloride have a -1 charge. The next step is to eliminate the spectator ions. That would be nitrate and sodium, and that leaves the net ionic equation of silver ion plus chloride ion makes silver chloride solid precipitate. So in the test tube, I have a clear colorless solution of silver nitrate, and I'm adding a clear colorless solution of sodium chloride. And when they mix, we see the immediate formation of a dense white precipitate, and that would be silver chloride. Let's try one more. Iron 3 chloride, aqueous, combined with sodium hydroxide, aqueous. Let's exchange ions. The inner brown line connects sodium and chloride, and we know that sodium chloride is soluble. What about iron 3 ion and hydroxide ion? Well, rule number 5 tells us that all hydroxides are insoluble unless hydroxide is combined with ammonium, barium, or group 1A ions. Well, iron 3 is not one of those exceptions, and so iron 3 hydroxide is indeed insoluble. So we can write for products sodium chloride and iron 3 hydroxide solid. Now this equation is not balanced. I can see 3 hydroxides on the right and only 1 on the left, and I can see 3 chlorides on the left and only 1 on the right. So if we put 3 NaCl and 3 NaOH, we will balance the equation. Let's now eliminate the spectator ions, sodium and chloride, and that would give us the net ionic equation of iron 3 ion combining with 3 hydroxide ions to give us FeOH3 times, and that's insoluble precipitate. In the test tube, I have a clear yellow solution of iron 3 chloride, and in the pipette I am adding clear sodium hydroxide solution, and when they meet, we see the formation of an orange-brown precipitate of iron 3 hydroxide, which in fact is an aqueous form of rust. A little more practice. Potassium iodide plus lead-2 nitrate. Let's interchange ions. The outer blue line shows the association of potassium and nitrate ions, and we know that the group 1A ion potassium and nitrate ions are all soluble, so potassium nitrate will be soluble. What about lead-2 ion and iodide? Well, rule number 2 tells us that all iodides are soluble unless iodide is combined with, well, there it is, lead-2, and so lead-2 iodide is insoluble. So we can write for products potassium nitrate aqueous and lead-2 iodide solid precipitate. Now this reaction is not balanced. As you can see, I have 2 iodides on the right and 1 on the left. I have 2 nitrates on the left and 1 on the right, so we should double up on the potassium iodide and the potassium nitrate, and now it's balanced. Let's eliminate the spectator ions of potassium and nitrate, leaving us with the net ionic equation of iodide plus lead-2 ion makes lead-2 iodide solid precipitate. In the test tube, I have a colorless solution of potassium iodide, and in the pipette, I have a clear colorless solution of lead-2 nitrate. And when they combine, you see the brilliant yellow color of lead-2 iodide precipitate. Last one. Here's sodium chromate aqueous solution and silver nitrate aqueous solution. Let's interchange ions. We know that the outer ions, sodium and nitrate, form a soluble salt, but what about silver and chromate? Well, rule number 6 tells us that all chromates are insoluble unless combined with group 1A or ammonium ions, and silver is not one of those exceptions, and so silver chromate is in fact insoluble. We can write for products sodium nitrate aqueous and silver chromate solid precipitate. Let's balance the equation. I see 2 silvers on the right, but only 1 on the left, and I see 2 sodiums on the left and 1 on the right. So if we double up on the silver nitrate and double up on the sodium nitrate, that's balanced. Now let's eliminate the spectator ions, sodium and nitrate, leaving us with the net ionic equation, chromate ion plus silver ion makes silver chromate solid precipitate. So in the test tube I have a clear yellow solution of sodium chromate, and from the pipette I'm going to deliver a clear colorless solution of silver nitrate, and when the two meet, it forms a brilliant brick red colored precipitate of silver chromate.
The procedures for this experiment are listed at the end of the document. I'll leave it to you to read them, but obviously you'll be carrying out some of the reactions that we have studied in this unit. And regarding the lab report, instead of a formal lab report, just include the following: title page, no theory. And for data and results, just complete what's here. So for part 1, complete and balance the reaction equations and name the type of reactions. If there is more than one type, if you can think of an alternate name, by all means write it in. For part 2, I've given you chemical names, and I'm asking you to write chemical formulas of each of these compounds, and then use the solubility table to state whether the following compounds will be water soluble, that is aqueous, or insoluble, S for solid. And finally, for part 3, I'm asking you to write balanced net ionic equations. Note I said net ionic equations for the following precipitation reactions. And that should do it. Thanks for watching.